And so thanks to Alex, and not this Alex, but the junior Alex, we've got a new way that I'm throwing up videos. We'll be throwing them up the same day as I record them from now on. And in the remarks section, as you go to the YouTube video, firstly, I'm going to post the YouTube videos on our website so you don't have to keep track of emails. And secondly, as you go into the description of the video, they'll be bundled with a list. It'll be a single video. It'll still be raw, but it'll be bundled with a set of time frames. So you can just click the time frame that corresponds to the description of where you want to go, and you'll jump right there. And that's the way I can get them up for you fast, without having to have you wait. But yeah, that's the only way I can get them up fast without having you wait for them. Questions on collaborative problems or on anything we've done so far? Yeah, Sabine, I feel it too. So let's head right into the new lesson.
So sir, I had a question, but it was a very long question. I was hoping maybe after class we could look at a problem, if that's all right.
I can't. I've got another class right after this. We can schedule another Zoom time, or you can just email it to me, or we can wait until next class when we'll have a little bit more. Today's class is got a fair amount in it, as awesome. Many do.
We'll do it later then, sir.
All right, fair enough. Okay. This lesson will at first seem new, but in fact, it's just a different way of looking at things that you've already talked about. So we're going to cover today Laplace transforms and circuits. So finally, this is why you're an electrical engineer and why we're studying it. And we will do a source. What we will do is go through an entire circuits 1 curriculum in half a class with source transforms, nodal analysis, mesh analysis. And this is the most important part of the lecture. This is where we're going to spend the vast majority of our time. And then I'll finish up with a very brief explanation of using MATLAB to solve actual algebraic equations, which is something you've not yet done. This is a really cool secret power tool you can use for all of your engineering classes. And it's enough to make you want to download it if you don't already have it.
Sir, so just a quick aside, for MATLAB, I know we were given a code when we had circuits 1 or your MATLAB class, sorry. But if that subscription ended, because I think it was only a year long, is there any way that we could get it through the department?
Yeah, so if you want to get MATLAB, there's instructions on the website. If it's not, let me know, but I've got a one-pager that explains how you can get MATLAB. I should have a one-pager that describes how you can get MATLAB installed for free in your laptop, either by going over, short answer is you can go over to the Barracks Help Desk and they'll just give it to you. If you're connected to the VMI network, and if you've got the VMI campus-wide license, you can go under the Help About license and just renew it, and it will renew it instantly. There's another instructions on the one pager that describes how you can even get it installed remotely if you're not around here, but it's easier to go to the Barracks Help Desk. And then the last way is there's a description how you can get access to a web version so you don't need to install anything on your computer using your VMI ID. But if you've already got it installed, the simplest way is to make sure that you're in an academic building and then go, it's something under Help About license renewal, and it will automatically renew when you click that.
Thank you.
Yeah. And if you don't see my one-page diagram on my website, let me know and I'll fix that.
just installed it on my new computer this winter, and I basically just had to go in and confirm my email that it was like my VMI email, and then it just gave it to me. So
It's a good deal. As I said, my license costs me about $4,000 with the toolkits that I have, and you've got access to the exact same computational version that I have, except that mine does not print out academic version at the bottom when I make printouts. Other than that, it's identical. I strongly recommend you not get it installed with all the toolkits. It will let you happily install 60 gigabytes of toolkits, which you don't need. You're not going to use any of them, and at least at an undergraduate level, and it will clog up your help horrendously. So help becomes unusable as you search for plot, and it comes back with help for 15 different toolkits versions of plot. Okay, let me begin with a blast from the past on source transforms. So I want you to recall that if you've got a voltage source, and if it is in series with some sort of impedance Z, and I'm going to use Z instead of R because we are in the frequency domain with this. So our Z could be a resistance or a capacitance or an inductance or any combination of those things. Then this is the exact same as a current source. And we can find that current source just by using Ohm's law to turn voltage and impedance into a current. And that impedance that was in series now becomes in parallel. And if that's true, you can run that whole process in reverse. To convert a current source in parallel with an impedance into a voltage source in series with the impedance. And once again, the impedance doesn't change, and the voltage source comes directly from Ohm's law. Current times impedance is voltage. And then there's two degenerate cases. And somebody tell me what the simplification of this degenerate case is.
The impedance goes away.
That's it. So there is no current source equivalent of this. But this says that the voltage is set by V between these two terminals, so that Z could be anything or nothing or infinity, and it doesn't change anything. So let's just set it to infinity, which takes it away. And then the current version of that is this. This guarantees that there's going to be I current going through this wire, no matter what that Z is. So then let's just simplify it to having a 0Z. And we're done. Okay, so we've got our degenerates and our normals. And armed with that, let's do an example of using Laplace transforms and source transformations. And this is our first learning block. So there's nothing new that I'm telling you. This is everything you've seen already. I'm just going to give a quick example. You've got a voltage source. I'm not going to get bogged down in the details. We're going to approach it from a high level question mark. You've got a voltage source that looks like, you've got a circuit rather, that looks like this. And these are all, this is not static currents and static voltages, but these are some sort of currents and voltages that are changing with time. And we want to analyze it. So let's say we've already taken it into the frequency domain. We have something that looks like this. I guess our C would now be 1 over SC, and our L would be SL if we're in the frequency domain. And this V and this I is actually some sort of function of V of S and I of S. Oh, we've got another C, so we'll call this C1, we'll call this C2. That seems pretty complicated at first, and this is our goal, to find V out. So from first principles here, how many nodes do we have that are unknown? Joe? What's your take on that?
Are 1, 2, 3. Or wait, sorry, just 2. Yeah, just 2.
Just 2? Let's see.
Actually, sorry, 3, because there's the one in between the current source and the resistor.
Yeah, so this is known. We don't know what this is. We've already called it V out, so that's nice. This one we don't know either, do we? And this we don't know. And I think that's everything. So right now, if we're going to use Nodal, we've got 3 nodes. By the way, don't forget that you only need a ground if you're doing Nodal. If you're not doing Nodal, if you're going to do simplification or mesh, you don't need that. How many meshes do we have that are unknown again? I'm going to say U, unknown, unknown. Ben, how many do you think?
There are 3, right, sir?
Yeah, so we don't know this guy. I'm going to use a different color to make it clear that we're doing a different kind of analysis here. We don't know this one. We don't know this one. Oh man, how are we going to handle this monstrosity? Ben, how would you handle this?
So for the left side, is it just I of the S for the left side, and then?
No, it's not I of S, because remember here, this is a single wire, and I of S is not all going to go through this wire. I of S is going to be divided. Part will go through this wire, and part will go through this wire.
Oh, my bad. Like I can do like a super mesh.
Yeah, there you go. Do that super mesh. And we can call this part of it I3, and then of course, if I of S is going here and meeting I3, then this part would be I3 plus I of S, and that would be your super mesh. Okay. All good ways to do it. So we've got 3 nodes. We've got 3 meshes. How about if we use superposition? How many circuits would we have then? John Arger?
I think it's comment on the one I didn't know. I don't know this one. I had mesh Nodal, but I'm
So superposition says that you zero all of your unknown sources, all of your sources except for one. You just keep one on at a time. You analyze it with the one that's on, and then you redo it again with the next one that's on, and you redo it with the next one that's on until you've got all of your independent sources done. You have to keep your dependent sources on all the time. So how many independent sources do we have?
just one.
Keep looking.
2.
2. We've got our V of S as an independent source here. We've got our I of S, which is an independent source here. So 2 independent sources, we'd have to turn them off and do them independently, just because now I've got you on the line. How would you turn off your voltage source? What would you replace your voltage source with when you turn it off?
Is that a short?
That's right. Be a 0 volt, so that's a short. And how would you turn off your current source?
You make it an open?
That's it. 0 amps for an open. Okay, you've redeemed yourself. So this particular problem seems kind of nasty, and I wouldn't solve it using any of those modes. I would instead I'd say, man, this looks. I would start simplifying things. I would simplify. I need a new color. I would simplify this, and I would simplify, and I do a source transform over here. Because my goal is to say this kind of looks to the right, sort of like most stuff is in parallel. And if I make this in parallel, then we'll have most of it in parallel. R2 screws it up. But if I do that, so we've got a V of S over R1, current source. And now we've got our R1. And now we've got still our output voltage. Important to write that down. We want to make sure we don't somehow change our output voltage. We don't want to source transform that away. We can ignore RSL because if we know I of S is pushing it through that wire, the inductor can't do anything. And now we've got this. Okay, now armed with this, this is almost all in parallel. Can we combine some resistors to make it all in parallel? Aiden, what do you think?
Yes, sir, we can.
Okay, how would we combine two resistors to make everything in parallel?
So we want to combine R1 and R3.
Sure. So we'll combine R1 and R3, and let's see. How many wires are coming out of R1? And how many wires are coming out of that simplification? We had 2 wires coming out of the simplification up here when we did our source transform. And we had 2 wires coming out of our simplification here when we did our source transform. How many are coming out of our R2, R3?
I'm sorry, I actually missed R2. So I don't think that we can simplify because there's 3 wires coming out of that.
You got it. Can't do it. That's it. So there's no way to simplify this R2 out of there easily. I mean, you could if you wanted to start off by simplifying, doing some sort of transform to this whole thing, and then you'd have a transform that you could do another transform with this guy, but directly there's nothing you can do. All right, so what I would do here is just stop again and say now, how many unknown nodes, unknown meshes, and maybe superposition too. So Chow, tell me how many unknown nodes do we have now with this guy? Chow, are you with me? Fochan? So my question is, how many unknown nodes do we have here? I'll put a ground down here. You always need to ground when you're doing nodal analysis and only with nodal analysis. And how many nodes are left over that you don't know?
4.
Where would they be?
Above the R1 and
Above the R1. Okay, so let's get above the R1. So let's see that. Let's get this whole wire. All right, so that's one of them.
and another is above the IS.
Yep, and there's another one up here. And so of course that's, when you're talking about a node, you're talking about everything along that wire. So that wire is pretty big. So that would be our V. Let's see, we've already called it a number. We'll call it VO. That's what we want to find. Here's our V1. And do you have any others? No, that's it. So just 2 unknown nodes. Preston, how many meshes?
Three.
Yeah, I think we've gone the wrong way with the meshes. So this one is, we know what this one is. It's set by VS over R1. This one we don't know. That would be an I1. This one we don't know, I2. This would be still our super mesh, I3. And then superposition, we still have, can we combine these 2 current sources since they're both current sources? Let's see, Charles, what do you say?
No, because they don't share the same wire.
Yeah, that's right. They're separated by this R2. So we're going to have to do the same 2 for superposition. But with a small change that we did, we've gone from it being unclear what the winner is in terms of analysis to making it very clear that it's nodal. And that didn't take very long. And now you can see what the next step would be. What I would do is I wouldn't do any of them. I would just keep simplifying. I would say we've got now this and these things in parallel. So I would just rewrite it as R1 in parallel with 1 over SC. I haven't changed the voltage across this top node and ground. So this is still V naught.
Sir, I had a quick question.
Yeah.
Before we go any further, before I get more confused, where the inductor that was in series with that current source on the right, where did
That's right.
that go?
We used the fact that a inductor, we use this simplification here, that an inductor in series with an impedance is just equivalent to the, that a current source in series with with any kind of impedance, whether an inductor, capacitor, or a resistor, doesn't, the impedance just goes away. Because the simplification is seen from these two nodes is that there'll always be I guaranteeing going in this side and out this side, no matter what that Z is. So that Z could be big or small, and it's still going to be I coming in or out. So why not simplify it and just say that Z is 0? And of course, inside, this is not a valid representation of what's inside those nodes, but from the perspective of these two nodes, it's the same. So from the perspective of nodes 1 and nodes 2 here, there's no difference between that and just getting rid of the inductor. Even though if we were asked for an internal voltage, say, across that inductor, that would not be a valid simplification. Does that make sense?
Yes, sir, it does. Thank you.
Awesome. Okay, so now we're just simplifying resistors here. We've got R2, which is still our lone holdout, but now we can simplify R3 with the 1 over SC2. And now we're just left with this. And if you redid your number of unknown nodes and meshes, this would be a whole lot simpler. But I might still be tempted just to take it all the way and now do my source transform of this side. Just checking, still only have 2 wires coming out of my source transform, so I can do that. And now I'd have my V over S over R1 with our thing we want to find, with our R1 in parallel with 1 over SC. Still have our R2 up here, but now we've got our R3 in parallel with 1 over SC in series with a voltage source, where this is I of S times whatever R3 in parallel with 1 over SC2 is. And then you can see that these are in series. I would add them. And then with one more source transform, now I'm left with everything in series. I finally got rid of that pesky R2. And now it's just simply Ohm's law. We've got 2 current sources. Actually, it's a current divider. We have 2 current sources. They add up, and they go between 2 resistors. And that would tell me what this current is. And then it's just Ohm's law to find V naught. Thumbs up? So it's often good just to sort of sketch those big picture things out there. And although the way I'm drawing it would be true whether we're in circuits 2 and talking about phasors, or we're in Laplace transforms and we're talking about Laplace transforms, whether we're in EE230 and talking about Laplace transforms. Okay, so that was a good overview about how source transforms work. Let's hit nodal. Between nodal and mesh, which do you guys feel most comfortable with?
Nodal.
Nodal.
Okay, good.
Yeah, nodal.
For some reason, every class has different likes and dislikes. And it's about even. I've seen more classes actually VMI that prefer mesh.
I mean, I prefer mesh, but whatever.
Yeah, sure. To each his own. So nodal is just an organized way of doing KCL. And remember, KCL is just an organized way of saying that the sums of the currents that exit your node, every node has got to be equal to 0. And so your steps are to choose your ground and choose it at your busiest node. You don't need to choose ground for any other method other than nodal. Had that question came up with the seniors just recently. And then you're going to label your unknown nodes with v sub i's, v1, v2, v3. Your next step is you're going to have to do something with voltage sources. Nodal methods loves current sources, hates voltage sources. You got to do something with them. And what you do depends upon whether or not they are connected. One side is connected to ground. If one side is connected to ground, it's probably easiest just to give an example of this. And we're in the Laplace transform domain, so I'm going to make mine a Laplace transform. Capital V1s, because we're in the frequency domain. Then we can get rid of our V1. This is no longer V1, it's just 2 over S, because this side is hard connected to ground. If it's not connected to ground, you're going to need the supernode. So now let's say we've got that same 2 over S, and it goes to a much larger circuit. This we've called V1, and this we've called V2 up here. You're going to now keep this as V1, because this voltage source says the top is 2 over S higher voltage than the bottom. This will have to be V1 plus 2 over S. And when it comes time to do your nodal analysis, you'll treat it as a supernode. So here, your supernode, your regular node ended right there. But this whole thing will be part of a supernode. Where down here, anything along this wire will consider V1 volts, and anything above on top will consider V1 plus 2 over S volts. All right, almost done. You'll do a KCL at every unknown node, or every unknown supernode. You'll never, having a known supernode doesn't make sense. And you'll never do it at ground. If you try to do it at ground, you'll get an equation, but you won't be able to solve your set of simultaneous equations. And then if you have any dependent sources, then you're going to give one extra equation. And it's often going to be Ohm's law based. Give a quick check to time. Okay. Good. So as a quick example, notice that for the capacitors, of course, it's always going to be something over S. This is a constant 6. So that means if it's a constant 6 in the frequency domain, it must have been a impulse in the frequency, in the time domain. And this kind of current source means it must have been a decaying exponential in the time domain. And if we wanted to analyze this using nodal methods, we choose a ground at the busiest source, because this has 3 things coming into it, and we don't need to do an equation at that ground. This is a known voltage. This is an unknown voltage, but we're going to do a super mesh, right? A supernode here. So we'll call this V1 plus 6, and that's it. And when we do our nodal equations, will only have two of them. Anyone want to see the super mesh, the super node equation, or shall we move on to mesh? Okay, then let's move on to mesh. So next is going to be Laplace transforms and mesh. Any questions about nodal analysis in general? It's a lot we scream through as a review. All right, so same idea with mesh. It's just an organized way of doing KVL, that we're going to sum all the voltage drops in every loop equal to 0. And to do it, no grounds necessary. Instead, we're going to label our unknown loops, I1, I2, etc. And you got to have a direction. And the direction is completely arbitrary. And just like Nodal didn't like voltage sources, we had to do something with them. Mesh doesn't like current sources. And for every current source, if it's not shared, well, then it really isn't an unknown mesh. If you've got this current source, then you know exactly what that I1, it has to be 2 over S. On the other hand, if it's shared, that's when you need to use the, well, there's a couple of ways to do it. The simplest way, the way I believe you've been told, is with the super mesh. So you start off with, say, something that looks like this. And you'll change it to something that looks like this. So the part that we're not going to change is I1 here. I just chose arbitrarily to keep I1. So I1 is in this wire, so it hasn't changed at all. That part's still I1. But now, as it's come together with 2 over S, this one would be I1 plus 2 over S. And it would stay that all the way through this outer loop. And of course here, now we've siphoning off 2 over S. So back here, we're back just with our I1. And then the rest is just like Nodal. Our next step is to, instead of doing KCL, we'll do a KVL around each unknown loop or super, I'm sorry, we're calling them meshes. And around each mesh or super mesh. And if we've got dependent sources, it's the same thing, one extra equation. Usually Ohm's law. And then it's a matrix solve. Let me give a real world example from a three-phase complicated circuit. And at the end, I think we'll have time for Philip's question. Say we've got our input voltage here. There's an R and a C. And at this stage in your life, you might not be able to do it rigorously with math, but you should be able, at least not by sight, but you should be able, when you're seeing this RNC, be able to see that if there's a really high frequency, it'll just short to ground through that capacitor, because capacitors look like shorts for high frequency, and for DC values, they're not going to go anywhere. The capacitor looks like an open, so it's going to pass those. So this already sort of looks like a low pass filter, since really high frequencies will just get shorted. This is a segment of a circuit taken from a three-phase brushless motor driver. So this C and this C they're the same values. This R and this R are the same values. This R and this C correspond to all those other R and Cs. And here's our V out. And we'll let R equal 1K, C equal 10 nanofarads, and we'll let RA equal 30 kiloohms. The question is, find the step response. In other words, find what happens when you pull the trigger. You're pulling the trigger of the controller for this three-phase system. Eventually, when we get back in person, I've got some great demos from this. I've got have I ever shown you, when you were rats, my three-phase car demo that's the size of a large dog? It's about 40, 50 pounds. Oh, I've got some great stuff to show you. Okay, so we need to find the step response to this. What happens when you pull the trigger? So the first is, because I'm a narcissistic SOB, use Squire's law for analyzing op amps. And do you remember that, anyone? What is it? Are you going to use KVL or KCL, and where are you going to do it?
At the output.
Oh, never at the outputs. Only at the inputs. And what is it, KVL or KCL?
Yeah.
KVL or KCL?
The KVL.
Oh, you're killing me, Smalls.
KCL,
All right.
yeah.
It is KCL and at the inputs. KCL at the inputs. You can't do KCL at the outputs, because despite the fact that it's not shown, there's really hidden power things here that can allow any kind of current to come out of here. So it doesn't seem to obey KCL at the output, but it does at the inputs, because what's the current that goes into the input of an op amp? Philip? Phil? How much current goes into an op amp?
Isn't it like 0?
Right.
Right? Nothing goes into the op amp?
That's right. For an ideal op amp, I going into it is equal to 0. And there's one other rule for ideal op amps. What is it, Sabine?
The voltage at the positive and negative terminal are the same.
That's it. The V inverting and the V non-inverting are the same if and only if one condition is true, and that is, Sabine, finishing it up. You're right, but not always. I mean, I could have an op amp here, and I've connected this to 2 volts, and I've connected this to 3 volts, and nothing's going to blow up in the op amp, but clearly V plus is not equal to V minus. So what else is necessary to guarantee this to be true?
Feedback loop?
Feedback. You got to have negative feedback. Oh, Jonathan, I'm sorry. I missed you. All right. So as long as there's negative feedback. And again, what that negative feedback does is say that if it's not equal, the output will swing wildly in the direction to somehow go through this feedback loop and make these two equal. All right, so if we're going to start off with the KCL at the inputs, we'll need to establish some KCL rules, right? So let's see. We know what, let's see, Vn is already labeled for us. We don't know what this voltage is though, right? So we'll call this V sub A. I could have called it V sub 1, whatever. It's all good. What are we going to call this thing? Is this going to be V sub B? Somebody correct me.
No, it would just be V sub A.
It's going to be V sub A again because we know it's got to be the same. Since there's negative feedback, those will be the same. Okay. How about this guy? Can we say anything about what's going on here? Or is this going to be just unknown? This will be unknown. We'll have no idea what that is. And then V out's already labeled. So now we can start doing our KCLs. And so our KCL, we're going to do it at the input, right? We're going to do it at the upper. So KCL upper gives us VA minus VN, VA over VN. So what we're trying to do is find first that current. And then to it, we'll add this current. So finding that first current in green, Jonathan, tell me finish that up for me. VA minus VN over
R.
Over R. And I'm going to have you do the next one. Do orange for me too. How much current is going out here?
Just VA over C.
VA over, yeah, it should be one, except for the fact that I was a little tricky here. Remember, it's really, I did that in time.
It's going to be VA times SC because you flip the 1 over C.
That's it. All right, so now we've done it for almost all of our nodes. We've done it this side, and we've just left with what goes into the op-amp, which would be, Joe, how much is going into the op-amp?
0.
0. So this lets us solve for V sub A as a function of Vn, which is known. And then we can do our KCL. Well, then we'll do our KCL at the lower branch. And can you give me the KCL at the lower branch, Dom? I'll start you out with VA.
VA minus VB over RA, and then VA minus 0 over R, and then VA minus VB over 1 over SC.
Which would be the same thing as times SC, and all that equals 0. Yep. And so now that you know what VA is as a function of Vn, now you can solve this for VB. And then last, now you know what VB is. You can find V out as just a voltage divider. V out's going to be equal to, does everybody see why you can find V out as a voltage divider? Chow, can you tell me what V out is as a function of VB? It's going to be your input, right? Times something over something.
times
Let's take a closer look at this. Let's see what this really means. When we say VB is at the top, we mean that we found what VB is. And we've got an R here, and we've got this 1 over SC over here. And we're calling the bottom ground. And we want to find V out. And we've defined V out as that voltage across 1 over SC relative to ground. So now with this different view, where this portion is exactly equal to what this is, tell me what our V out is.
R plus SC.
R plus 1 over SC, yeah. That's in the denominator, that's always the sum. And then the numerator, it's
SC, 1 over SC.
1 over SC, that's it. And that's it. And now you can, and that is solved for V out. And that's the way to solve this entire Opamp sample. And if you do it, yeah, and that's it. So there's our Opamp example, and everything else is just algebra. Any questions on that? It looks a lot harder until you actually start to work through it. All right, let me show you some magic. It's time for a magic trick. Wouldn't it be great to solve something like VA minus 1 over S, let's see, all over R plus VA times S times C equals 0. Wouldn't that be kind of cool to just instantly solve using MATLAB? Not numerically, but algebraically. Give me a second, and I'll see if I can share my MATLAB screen, and we'll do just that. So I wish I could share two things at the same time. I can't do that. But I'm going to show how to solve that equation I just wrote. I'm going to use some new commands in MATLAB you haven't seen before. If you want to do this on your MATLAB, you do need one toolbox. You'll need the symbolic algebra toolbox. And you start off by describing your symbolic variables. So there's your symbolic variables. We'll say it's VA, S, C, R, RA, and V1. No commas. And when you do that, on the right-hand side, all of a sudden they show up that these are going to be symbolic variables. And now let's create your equation. Maybe you got multiple equations, so I'll call it equation 1. And the terminology is you've got to put it inside a curly bracket. And now you just type your equation normally. It's minus VA minus 1 over S, we said. And all that we're going to divide by R. And we're going to add to it VA. This is the only thing that's, and just like MATLAB, it doesn't understand implicit multiplication. So you've got to say VA times S times C. When you're setting something equal to 0, you've got to use 2 equals. A single equals means you're going to rename it equation 1. 2 equals means one side of the equation is equal to the other. And as we began it with curly Q brackets, we end it with the curly Q brackets. Whoops, yeah. I could define a capital C here and a lowercase c here. So the program is smarter than I am. And then to solve it, we're going to take that equation. It just means lay the equation flat. And solve it. Once again, it's equation 1, and so it solves it. And that's pretty cool. So that instantly found what VA is. We asked it to solve for VA. This is what it is. That's a lot of algebra that went in there. It's even better than this. If you wanted to do an inverse Laplace transform of it, you could do that of the answer that we just had. And if we use our independent variable of t, it just found the inverse Laplace transform. That is cool. Once you get used to the weird syntax that the symbolic solver uses, you can use this on homeworks. You can use this to check your answers. You're not going to be able to use it on exams or on the FE, but you can. It's a great tool to track the complicated algebra.
Wait,
Okay.
so sir, the add-on was called Symbolic Math.
Symbolic math. That's right.
And do you need anything for the inverse Laplace one?
No, that's the symbolic math too. It does a lot more than just this. If you had the problem we just talked about with the Opamp analysis, you could have it solve multiple equations just by putting them in brackets up here. Really useful to know. Now, all that said, if I had to solve symbolic equations for a living, I would use MATLAB. I would use rather Mathematica. And we have a campus-wide license for Mathematica also. But rather than installing a whole nother package, the stuff that we do is MATLAB symbolic solver can handle easily. And since it's built into the package, it's a great thing to have. Okay, questions about this? If none, we've got some time to go back to Phil's question.
Sir, I just had a quick kind of off on a tangent question.
Sure.
Do you have any classes that you would recommend that are MATLAB or Mathematica based that we could take for credit that you would recommend?
No, I don't. At your level, taking the only time that I, in my opinion, and it's kind of a snooty opinion being an electrical engineer, but the only time that I think any classes should exist on how to use a program are at the freshman level. After that, you guys really can just crack the book and learn it as you go. I've seen courses offered in the math department for Mathematica and for MATLAB, and it's kind of insulting to your intelligence. I mean, just fold it into what you already know. I've seen classes in how to use Photoshop, and again, the best way to learn these things is just to go through help and go through a few video tutorials as you encounter the need for them. And that'll get the information in your head better than any kind of class anyway, because you'll actually be using it to solve the kind of problems that you need to for electrical engineering. But that notwithstanding, if I could wave a wand and push down knowledge into your throats for any set of software for industry or for graduate school, I would say the software that you should be able to use would be MATLAB, both programming and how to make plots using functions so that you can recreate those plots easily. That's incredibly powerful. I would say either Mathematica or the symbolic solver in MATLAB. For what you guys do, either one would be perfectly sufficient. Mathematica is just drop dead gorgeous, but Mathematica versus MATLAB is sort of like the difference between driving a Ford F-150 and driving a Ferrari Testarossa. You want to drive the Ferrari Testarossa. It has incredible sex appeal. That is totally Mathematica, but no one's going to pay you to drive it. Whereas the Ford F-150 gets the job done. It's a big brute. It works reliably. That's MATLAB. In my life, I've never known anyone to have used Mathematica to make money. Not saying it doesn't happen, but I haven't known anyone. I've known tons and tons and tons of electrical engineers who use MATLAB to make money. I would say JavaScript, super important. Visio, incredibly important, and Photoshop. Those would be the minimums that I would say you'd want to be familiar with to go into grad school or industry. Instead of Visio, you could also use Illustrator, but Visio tends to work out better for engineering drawings than than Illustrator. Illustrator, again, way more powerful than Visio, but it's the same thing like Mathematica versus MATLAB. Visio is just a workhorse, and Illustrator is amazing. It can do incredible things, but it's not as good to quickly pump out lots of standard engineering drawings as Visio is. Any others? Okay, Phil, talk to me.
All right, sir. So the question I had, it was less of a conceptual question and more of just a clarification question. But it was about the Laplace transforms when we're going.
Oh, and let me interrupt everybody. Since this is really, we're now on to the optional question stuff. If you want to go, you're free to go. Okay, sorry, Phil.
No issue. I'm trying to pull up the question now. It had to deal with being in the with like the imaginary roots.
Yeah.
Question about transforming that, and if you could, I don't know if there's a problem you have at hand or something you want me to.
No, but I'll just make something up at random. Let's say that you've got a output voltage, and it's equal to 2 plus S over, and you've already found the roots, and you found the roots, and they're going to be equal to -3 plus or minus J2.
Right.
So therefore, we're going to have something that looks like S plus 3 minus J2 over S plus 3 plus J2. So even though the roots have a minus, here it's a plus, because what the root means is when you put this into here, the pluses, 3s will cancel out and you'll get a 0.
Right, right.
And the question is, how do you quickly get that into, how do you quickly do the inverse Laplace transform of this? And here's how you do it. You firstly say that you know it's going to be equal to A over S plus 3 minus J2 plus A complex conjugate S plus 3 plus J2, where the secret is that these signs, the first ones you write, are always going to be opposite. And even though this is algebraically true, as far as you care, you're not going to worry about the second part at all. You're just going to focus on the first part from now on.
Right.
So,
I was curious why you even drew that out, because we don't really use that at all for solving for A.
You certainly do. You certainly do need to solve for A. Absolutely.
Right. But we don't use the complex. Like why even write that second term out?
Because it's mathematically correct.
Okay.
It's mathematically required. If we just said this is equal to this is equal to, you can't see my hand on the screen. If we just said this is equal to this part, that would be mathematically incorrect. It's just wrong. And if someone was to solve it using a different way by multiplying out the bottoms here and matching terms, they would get something that showed that it was wrong. So to be mathematically correct, I do this. But then the next step is we're going to find out what A is. And to find out what A is we cover up that associated term here. So we're left with everything else, 2 plus S over S plus 3 plus J2. And we'll substitute into that our root, our corresponding root to the part that we covered up, which is -3 plus J2. Quick check. What we're substituting in better have different signs. Shoot.
Right. My big question was, what happens when we have an imaginary root along with like an S attached to the back of it? Because I think there was there's a CP or something, and that kind of threw me for a loop for a second.
How about that?
Yeah.
We'll do better than that. So now our roots are going to be this, 0, and -3. So we got a lot of roots. Agreed? We got 4 roots to that sucker, that denominator. It's a 4th order. It's a quartic. So now we're going to have to add more things down here. Okay? And now that we've done this, our new A is going to have to be equal to our whole piece, but with that first part, that first root covered up. And every time we see an S, we're going to replace it with our root. So now it's just an algebraic substitution. And similarly, we're not going to bother to find our A star, but we will find our B. And we'll do it the same way. We're going to substitute, we're going to cover up just the corresponding root to b. We'll be writing here for a minute. And we're going to substitute in s goes to 0. And then last, we've got our c to find out. So we're going to write out our whole thing except for the corresponding root, whoops, except for the corresponding root to the c part.
Right, and when I saw that in the CP, I think it was the CP, the answer for B and C, instead of substituting into the imaginary part, they took the function because it's equivalent to whatever was before that, and solved in there. Can you can still do that?
So let me do it. So let me do it. Let's say I'm just making this up on my own. So I'm going to start calling this a different color to show that I'm making this part up on the fly. But let's say our A, we always want to write our A's in polar form. So let's say it's equal to 7 at an angle of 15 degrees. Okay? And then let's say that this equals -4, and let's say this equals 13. So now, from this, we can write our answer. This part we can directly write as being equal to 14. We always multiply the 7 by 2 times e to the real part of the root, cosine of the imaginary part of the root is our frequency, plus 15. So in other words, corresponding, this 2 corresponded to the imaginary part. This 15 corresponded to that 15. This 14 was 2 times that 7. And the last part is this 3 corresponded to, that -3 corresponded to that -3. And then this -4 corresponds to a -4 over s part, right? That's what this said. So this corresponds to a -4 u of t. And then this 13, that corresponds to a 13 over s plus 3. So that would correspond to a 13 e to the -3t. And so now we would add all that together, multiply it by a u of t, and that's our answer.
Okay, so when solving for B and C then, instead of like using the imaginary parts, could you like go back per se and use what it was
absolutely, absolutely. So realize that this thing came from an s squared, and I'd have to do it quickly. I can't.
Right, that's fine. I think I understand what you're saying though, but that makes sense. Thank you, sir.
Yeah, that's exactly right. For those of you who didn't follow Phil's question, let's say I can't do the multiplication on the top of my head, but let's say I'll do this in green again to show I'm just making it up. Let's say that came from s squared plus 2s plus 10. Then instead of doing this, just put in that s squared plus 2s plus 10, and that over here, that s squared plus 2s plus 10. And that's a whole lot faster to find your solutions to.
And then, sir, I had one last question about the homework, and then I'll be done.
Sure.
I'll let someone else have a turn. But for the Connect homework last night, I put in all the answers. For whatever reason, I got most of them right. I got all of them right except for one part, and that one part it didn't like when I put in. I guess I put in -1 divided by 2. But the answer was like -t/2, which is the same thing. I just wasn't trying to put it in. It ended up marking me wrong, and I wasn't
-1
sure.
over 2 versus t over 2?
Right, because the t was already part of the equation, I believe. But it like when I ended up submitting it, I thought I put -1 over 2. It ended up submitting it as like -1.0 divided by 2, and I wasn't sure if I'd accidentally like added something. Again, it might not matter because the homework, I mean, it was just 1 point off, right? It was like 1 point, a little over a point off, and the homework doesn't count for much, so maybe it's not worth fixing. It just seemed like it was a little strange.
Do you remember off the top of your head which homework problem it was?
It was the first one, because I got the rest of the parts right. It was just that one.
So it's probably
I took a screenshot of it too, because I was curious.
Yeah, send me the
Yeah, I mean,
screenshot and I'll take a look at it. And I'll see how, if everyone got, for the vast majority of people got P1 wrong, then that indicates there's it has an incorrect solution. And if only if a quarter of the people got P1 wrong, then that indicates just something odd with the way that it's a disconnect between the way that you expect to write the answer and it expects to see the answer.
Okay, awesome. Thank you so much. I appreciate your time.
Sure, I appreciate you debugging things.
yeah, I mean, I just want to add to that. Like, I think like the connect homework. I don't think this would well would like think like putting in like square root of things. Like for some reason the answer just turned out weird. I'm not sure why. So like instead of turn it into like decimal, I just put it in like in form of square root, and then I don't know, it just did some crazy thing.
Did you have the same problem for P1, or was your problem with a different issue?
Yes, so the -1/2, and then I think it's for question 1 that I'm trying to put in like in form of like I think 16 and then square root of 3, but then I don't know why, but at the end it said it wrong and it turned into something different. But I mean, I did it the second time.
You're having problems with P1 also, huh?
You're mixing up
Right,
not caring and doesn't.
But I did it the second time, and then I turned it into like decimal. Like I think it's I don't remember exactly.
So instead of -1/2, you tried -0.5 as an example, and then it seemed to. Okay. I'm going to. Ben? You and Phil are among my top students. What is your impression of Connect versus Canvas? Because I've been seriously thinking about getting rid of Connect entirely and going just to Canvas.
Personally, I feel like it's kind of like balanced out. So like giving homework in Canvas and Connect, because I know that some people like Connect homework because they have multiple like try of that homework, like attempt to that homework. So I feel like it's kind of balanced out for us, like different kind of homework. And
so there's frustrations with both, but there's positive parts to both. Is that what you're saying?
Oh, right, sir.
So you're not willing to give up either. Because
that's what I say.
Because I'm telling you, I've faced more problems with the Connect platform these past 2 years, and unless I hear students say that they like aspects of Connect, I seriously think I should just get rid of it.
But, I mean, I think the aspect that I think people like about the Connect homework is like you give us like multiple attempts with with the highest grade that we got. So I feel like that's the aspect that a lot of people like about the Connect homework. So like maybe if you can give like maybe some homework on Canvas that like some of them you might only get one attempt, but maybe some with unlimited. I mean not unlimited. Yeah, maybe unlimited attempt or like 3. So I feel like that's good work too, sir.
I mean, I'm not against unlimited. There's no difference to me in my mind between 3 attempts and unlimited. No one's going to work at more than 3.
I mean, yeah, I think
I hear what you're saying. That's a good point. I hadn't thought about that.
So I think there's a possibility of get rid of Connect, but if you can like have some of our homework like on Canvas, like with unlimited attempt, I feel like that's kind of like also like what's happening right now.
Like, here's the problem with doing unlimited on Canvas as opposed to Connect. In Connect, every time you redo the problem, it gives you a new problem. It tells you how to solve it, but then it gives you a new problem to practice it on. In Canvas, I don't have that ability. In Canvas, after you solve a problem once, the 2 choices are it either gives you the exact same problem to solve or it doesn't. And I'm not against letting you solve the same problem again and again, but if I do that, I can't give you the answers right away, right? Because once you have the answers, it's kind of silly to say, here's the answers, solve the problem. And the answer says 2, you just put in 2, it's done. And so I wouldn't be able to give you the answers then. Would you prefer that if I didn't give you the answers after you solved it in Canvas, but gave you extra submission attempts?
I would say I'm kind of like the way Connect doing stuff like kind of like changing the problem a little bit. So if we stuck with one problem, like we we
Yeah,
kind of like
yeah.
see the solution at the end and then try to work it again with different set of numbers. So
yeah. I'll be honest. I kind of thought that was only for the really. I didn't think that students like you're at the very top of the class. I didn't think students like you found that valuable. I thought it was too easy for students like you. But you also find it valuable. So let me rethink about how I'm doing this, and let me see if there's more. For now, I'll keep doing it the way we're doing it. I'll give you guys a mix, and I will see if there's a way that I could, if you get a problem wrong in Canvas, serve up a different related problem and let you try it.
right, sir. I think like if that work out, I think that could be like perfect for you too, because you said there's some problem. You encounter some problem with Connect homework.
Yeah, I've been having problems with Connect, as have you. It's just difficult to set up. But Canvas I don't think Canvas gives me the capability. I don't think. I'll look into it. So that what I really want to do is have a programming problem in Canvas that if you get it wrong, then it gives you the option to take it off, to take it wrong, or to solve another problem. And then every new problem it gives, I would have to create a new problem, which is fine with me. Create the new solutions for that new problem, which is also fine with me. But let me look into it. I'll see. I don't think Canvas has the capability, but we'll see.
Oh, yes, sir.
I appreciate it, Tran.
All right. Thank you, sir. Have a
Take care.
nice day, sir.
You too. Bye-bye.